Hello and welcome to another video. So in this video I wanted to discuss about digit dynamic programming. So we'll discuss what problems it solves and how to approach the problems involving counting numbers in particular range with some given property. So let's start. So let's start with what kind of problems digit DP is going to solve for us. So in particular, the problems are generalized as you need to count some numbers with some given conditions. We'll go through some examples after this. So you might be given arbitrarily large ranges, and you need to count some numbers with a given condition in that ranges. So let's go through some sample problems. So you might be asked to count the numbers in the range from L to R, and the sum of digits should be some given number k. And another thing is this L to R can be very large, up to 10 raised to 5. So in general, these problems cannot be solved using naive approach just by iterating through a for loop. So yeah, so let's see the next one. Next one is count numbers in that range with at most 8 distinct digits. So each number is characterized by digits 0 to 9. So you might be asked to count the numbers with at most 8 distinct digits. Then next one is you might also need to solve for some of those numbers with the given condition. So for example, the condition here is the number only has the digits 1, 2 and 3, and you need to count the sum of all those numbers which have only digits 1, 2 and 3 in that range. The next example is it asks that the digit d is appearing in that number exactly k times. So there can be many different variations for this problem, so I've just taken out this for general use cases. So yeah, so this should give a clear idea what kind of problems digit DP is going to solve. So next let's discuss how to approach such problems and what are the observations that we can use. So what ideas from dynamic programming we can use in counting the numbers. Okay, so any number can obviously be treated as a sequence of digits from 0 to 9, and this sequence in our example, in our problem statement, can have length up to 10 raised to 5, as we saw in this. This length is the power of 10 present here. So the length of those numbers could be very large, so we need to treat them as sequence of digits. The next observation is counting numbers from L to R is same as counting numbers from 1 to N and subtracting the numbers from 1 to L minus 1. So we divide the problem into two subproblems which are similar. So we make the problem statement, modified problem statement as counting the numbers in the range 1 to N. Here N is R or L minus 1, and we need to subtract those to get the final answer. So to find so how do we solve this problem now? So whenever we are going to iterate over all the numbers from 1 to N, we create all the numbers from 1 to N from left to right, considering its most significant bit to the less significant bit. This is because whenever we are comparing two numbers, we always check their most significant bit. If it is equal, we move on to the next one. If they are not equal, we check whichever has greater digit is a greater number between them. Hence it is require that the digits that we are going to fill from left to right are ordered and help us to identify they are between 1 and n. So let's represent the string form of n as d1, d2, dk, where k is the length of the decimal representation of n. Now we construct a sequence of digits from left to right, um, such that the generated number is less than equals to n. And how do we ensure that? So as I told earlier, so let's say we are comparing two numbers x and y. X is less than y only if the first place where x that digit is not equals, they are not same, and the first one has a smaller digit at that position. So the first position where different digit occurs in both the numbers is going to decide which one is greater among the both. So based on this observation, let's take an example. So let's say we want to iterate over all the numbers from 1 to n, right? And we are starting to filling the digits from this position, which is the most significant bit. Now if we fill a 2 here, then the resulting number that we are generating is greater than n, which we don't want. So what values can be put here are determined by this set 0 and 1. So that ensures that the number that we are generating is less than n. Okay, so filling the first position should be from this set 0 to 1. If there was a 7 here, it would have been 0, 1, 2, 3, 4, 5, 6 up to 7. So this is the first observation. The next one, after we have filled, let's say at some point we have filled some numbers, and now we want to fill an intermediate position. So let's say until now we have filled up to this, and we want to fill the star position now. Now as you can see, we have never put any digit which is less than that corresponding position digit in n. So until now we haven't made x less than n, hence it has to be between 0 to 4 only, because that guarantees that x will be less than equals to n. Another scenario that we are going to consider is, let's say we have position 1, 1, 3, and now we want to fill a star here. Now as you can see, this position already ensures that x is less than n, because it is the first position where the digits differ and this x has a smaller digit than n at that position. Hence we can fill any number here from 0 to 9, any digit here from 0 to 9, because x less than equals to n is already ensured. So these were the two observations that were important for iterating over all the digits that can be possible at a particular position. So these three examples illustrate that. So let's go through what we have seen. So our task is to generate a sequence x, as we were doing here, x which has a length k. The length of that sequence is k, and the first position where those digits differ should have the digit in x less than digit in I, digit in the given number n. And based on the examples that we saw earlier, at any position I, we will have choices from 0 to 9. If there is already a position j which is previously chosen that has a smaller digit at the corresponding position in n, or it could be from 0 to the ith digit in the given number if we haven't chosen any smaller digit earlier. This all positioning of numbers makes sure that the number that we are generating from left to right of length k is less than equals to n. This condition is a little bit similar to lexicographical comparison as well, so that is also helpful. So based on this condition, let's uh, find out a recurrence relation or function that is going to solve our problem. So let's take an example. Let's say the problem is counting numbers in the range L to R, for which the sum of digits is the given number k. So based on the uh, calculation that we used here, we are again mentioning that the answer from L to R is answer from 1 to R minus answer from 1 to L minus 1. 1 is neglected here because we are counting all the numbers, positive numbers from 1 to n, and this solve function is going to give the count of numbers in 1 to n that we want, which is count of numbers in 1 to n with sum of digits as k. So for implementation, we first convert n, which is the parameter of this solve function, to the string format. It might be given as string format depending on the constraint of the problem. So the first step is to represent n as a string, and let's say d is the number of digits in n, which is the length of that string. Now we start constructing the sequence from left to right at index 0. As we saw earlier, we start at index 0 and we put all possible digits which are valid at that position and move to the next position, and so on recursively. So let's say we are storing our answer. This function is returning the answer that we want if we start at index 0. So let's say go is the function which is going to calculate. So I have written the definition here. This function returns the count of numbers less than equals to n starting from index equals to id. So this index id is initially 0, so that it will find out all the possible digits that can be placed to create a sequence of length d, and other parameters denote the small taken is going to denote whether we have already taken a smaller digit at a corresponding position, which is going to help us in resolving this condition. So if our recursive function is at the state where we are currently at a star, then small taken will be true, because at this position a smaller digit was inserted in x. So that state is going to help us in inserting valid digits, and sum of digits is the sum of all the digits that we have constructed until now up till index id, and this is going to help for our problem because we want that the sum of digits of the number is k. So in the end, after we have generated a sequence of length d, we will check that the sum of digits is equals to k. If it is equals to k, then we have generated a valid number, and we return a we say that this number is valid and add it to the answer. So these definitions are for the states of this function. id denotes the index of the constructed sequence, small taken boolean denoting whether we have taken a smaller digit, useful to know that what digits can be inserted at any position id, which is a particular state of this function, recursive function. Next, sum of digits, as I told earlier, the number that we are generating has some digit sum which needs to be maintained so that it is validated once the entire number is generated, which is at index id equals to d. So this function is going to return the answer, and we will call this function with these initial parameters. Go 0 denotes that we are generating the number from MSB, which is position 0. False denotes that small taken is initially false, there it is the first digit, there is no smaller digit taken, and sum of digits initially will be 0. So now we have we are yet to implement this function. We know what it does, so let's go ahead and see how it is implemented. So this function is going to return the count of numbers. So this id and small taken will be the common states, because they are going to ensure us that the number that we are generating is less than equals to the number that we want based on this condition solve n. Okay, so base conditions when we reach to the end, or whenever we have constructed d digits, which is the size of the string representation s of n, then we check whether sum of digits is k. If it is k, then we return that 1 means the count is 1, there is one number found with sum of digits equals to k. And so now this condition denotes what all digits can be inserted at the position id. So as you can see, whatever we concluded here is reflected in the code. So it will be 0 to 9 if a smaller digit is already taken, else it will be 0 to t add digit. I have written as it is. So if a smaller is taken, then the limit for the maximum digit that can be inserted in that position is 9. If it is not, it is the ith digit in string representation. So I will insert all this digit, I will go to the next index, and I will also update the small taken value for the next state. So small taken could be any one position, so we need to take or for finding out whether there is at least one position where a smaller digit is inserted, and sum of digits will be incremented by digit for the next state. So this recursive function will go ahead and go through all the indices from 0 to size of s, and add the count of valid numbers from inserting all these valid digits from low to high. So as I told earlier, so this condition helps us to find out what all digits can be inserted at the ith place, which depends on this state small taken. And this state can be modified depending upon different problems. So you might be asked to find out product of digits in a given range. So this will be product of digits, and in the end you might be asked that product of digits should be equals to k. So this condition will remain same, but sum of product of digits will be multiplied by the digit which we are inserting. But it is a different problem, because in this case leading zeros are not affecting sum of digits, but leading zeros will affect product of digits. So it is a completely different problem, and depending on that you may need to include different helpful states, which are going to help you to count the numbers in that range. So whenever you are reaching the last position, you need to check whether those conditions are met and update the answer accordingly. So regarding the time complexity, initially if you just do a for loop between L to R, it will be impossible to, it will be too huge and not computationally possible. So for a number like this, the time complexity is too much for any computer to resolve. So but our dynamic programming approach, if you add memorization here, the time complexity will be reduced to the number of unique states, which is the values id can take is up to length of s. Then small taken is a boolean, so it is a 0 1 field, and sum of digits is k, which is given in the problem statement. And in each iteration, in each state, we are going to at most 10 digits, so that factor will be multiplied here. In all, it is a huge improvement, because even if a number is as huge as 10 raised to 10 raised to 5, the time complexity will still be 10 raised to 5 times k. which is given in the problem statement. Hence, this is a very common approach for solving counting problems, and I hope the concept is clear. And depending on different conditions that will be given in the problem statement, you may need to think of how these variable states can be modified so that the expected conditions are met. So for this problem that we have chosen, it was trivial to store sum of digits because it was asked to count numbers with sum of digits equals to given number k. But depending on different problems, it will be different. So this was this problem. So let's say this is the new problem. Let's say this one, and I will just tell you what all states will be required for solving this. So count numbers in this range having the digit d in its decimal representation exactly k times. So for now I will assume that d is positive, because considering the leading zeros is a different and non-trivial use case which you need to think of first. So for this, what you can do is store the count of a digit in the state. So for example, d was given as 6. Then what you will do is store instead of sum of digits, you store count of 6, initially 0, and whenever you are inserting digit which is equals to 6, you add 1 to it and pass it on to the next state. And once you reach the end of the sequence, you check whether the count of 6 is equals to the one that is expected, which is k, which will be given in the problem statement. Yeah, so these two states will be common depending on most of the problems, and you have to think of what extra states you need to store. Yep, I guess that's it. We can go through a practice problem from Codeforces. Okay, so in this problem, you're asked to count the numbers from L to R, L and R up to 10 raised to 18, and the decimal representation contains no more than 3 non-zero digits. So then the number of non-zero digits is at most 3. That is the condition that they have given. And since we are only counting non-zero digits, so again the leading zero factor is to be neglected because those are irrelevant according to the conditions that is given to us. So let's go through the solution for this, which is very similar to what we saw earlier. So they have test cases. For each test case you are provided L and R, and again we are going to represent our answer as count of numbers from 1 to R minus count of numbers from 1 to L minus 1. We convert it to the string. This is memoization. Then our answer will be, we are introducing a new state, non-zero digits, which was expected in the problem statement. As you can see, the condition that was given was that decimal representation contains no more than 3 non-zero digits. So we need to know the number that we are generating, how many non-zero digits does it have. So it is important to store that in the states. Whenever the number of non-zero digits exceeds 3, that number is invalid, and we can simply return 0 from that case. And if we have generated the whole number, which is the length of the string representation of n, we return a 1 from it, saying that we have found one number and add it to the answer. And again, the conditions that we saw earlier, it is exactly similar to that. If we have taken a small digit earlier, the numbers that we can insert at this position is from 0 to 9, else it is from 0 to the 8th digit, and we add to the answer this condition. Non-zero digits will be whenever the digit is non-zero, we add to this state and pass it on to the next recursive call. It's literally the same, but just these two conditions, and what needs to be stored in the state has to be altered. And this is a simple memorization approach. You initialize all the states with -1, which is an invalid answer that can be returned from this function. So whenever the value present in this memoize table is not -1, you know that this is already computed and you can return from that instead of recomputing. Literally exact same solution with what we saw here, just the state was changed. Next problem is a little difficult, and its solution has a little different approach for going through all the numbers from L to R. So let's go through that. Okay, so I created this problem 2 years back. Let's go through it. The count number of integers in the range L to R with the following property: number of digits with odd frequency is X and number of digits with even frequency is Y. Here frequency of digits in an integer is count of number of times it occurs in its decimal representation. If a digit t occurs in a number 0 times, it means it is considered to have even frequency. Okay, so problem is pretty clear. For each digit you need to find out how many times it occurs in its decimal representation. So let's say a number is 112233, then 1 occurs 2 times, 2 occurs 2 times, 3 occurs 2 times, and the parity of those frequencies needs to be equal to this number. So if you might have been given that the number of digits with even frequency is 3, then that 112233 is going to be a valid number for us because all those digits have even frequency. Okay, so the basic idea is to store one observation is clear that we only need parities of the frequencies, right? Either it is 0 or 1 mod 2. So instead of storing the all frequencies, we just store whether the parity is currently even or odd, and the number of unique digits is at most 10, 0 to 9. Hence we can use a bit mask to store the parities of frequency. So 0th bit will store whether the frequency is even or odd based on the binary representation of it. So whenever we insert some digit, we flip its parity because adding a frequency is changing its parity from even to odd or odd to even each time. So the basic idea is to store the frequencies, parity of frequencies in a bit mask, and store that bit mask in a state. And once you have completed all the positions, reach the end of the string, you check whether the number of zeros in that bit mask is X and the number of ones in that bit mask is Y, which will be provided in the problem statement. Okay, so this is the implementation for that. This implementation uses a different approach, which is it doesn't give you the answer using first 1 to R, count numbers from 1 to R, then subtract numbers from 1 to L minus 1. It just appends. First of all, it makes the length of L and R equal. So by prepending zeros, leading zeros in L, and once that is done, it is going to insert digits from MSB to LSB obviously, but depending on two states. So for initially the solution that we discussed earlier, we only used one state, which was small taken, but in this case when you store two states, big A and small b, that will help us to directly go through all the numbers between L and R. So you can go through this implementation. I will provide a link for this in the description. So again, I will just tell you what the other states represent. So again, in this case, it might be the case that leading zeros are also accounted in the frequency, which we don't want to consider. So to handle that, we also need to store this state, which is whether we have taken a non-zero digit or not. So based on that, if we have taken a non-zero digits, then only we can update the frequency mask. So this will go through the digits that we can put at index 0. We only update the frequency mask if the digit is not 0, because the first if you insert a position at if you insert a 0 at position 0, then it is a leading 0, which doesn't account in the decimal representation of the number. Hence we only account it whenever the digit is non-zero, and we pass it on to the function and we compute the answer from the first position. So again, these two conditions are according to the problem statement. Odd count will be the number of number of ones in binary representation, which can be found out using this function, and even count will be the number of zeros. And this is the base condition, which is going to validate whether we have found a valid number or not. This is memoization. Again, these two conditions are going to help us determine whether the number that we are generating is greater than equals to a and less than equals to b. You can go through this to clearly understand it. And again, this next frequency mask is updated only when if we have a non-zero digit taken, or we are currently inserting a non-zero digit, so that leading zeros are not accounted in this frequency mask. And similar to what we have implemented, we add it to the answer for all the next positions. Yeah, so that's it for this problem statement. It was a little difficult, and the solution had a I just wanted to show that this way is also possible for iterating through all the numbers from a to b, instead of storing the answer from 1 to r and subtracting answer from 1 to l minus 1, which might be difficult for some problem statement. So here, as you can see, the input was given in string format. So you can't simply just say that find the answer from 1 to r and subtract the answer from 1 to l minus 1, because you need to perform l minus 1, which is subtraction on a string. So you also needed to handle that. It might be non-trivial or could be time consuming depending on the implementation. Hence this approach is also helpful. You don't need to perform any operations on the ranges L and R, which were required here. So if L and R would have been given in string format, this L minus 1 need to be computed and then stored in string format and then given to our solve function, which might be non-trivial in depending on the programming language that you are using. Usually whenever L and R are between 10 to 18, it can be represented in a 64-bit integer, and you can directly perform the operations and then convert it into string format. But if the numbers are as large as 10 to 5, then it might be difficult. Hence this approach is also helpful sometimes. I will provide the link to this and the other solutions in the description. Yeah, I guess that's it for this video. If you like the video, do share and comment if you found it helpful. Thank you.